Okay, so the immune system. So this is a collection of a very large number of cells, and they can be, rather than classifying them, I'll just mention a few. So first we have the T cells and B cells that are, okay, T cells and B cells that are, their job is really to eliminate. The B cells are going to tag in microorganisms. The T cell's job is to kill them. The problem with cancer is that it's not really a foreign body, it's a part of our body, so it may not really give signs that it is dangerous and to be killed. Then we have dendritic cells that they are a sort of, when there is a problem, they go from the problem area into the lymph node and to try to bring in the T cells and the B cells. And then there is the macrophages. These are the most fascinating, the most plastic of all the cells. So we are going to be concerned mostly with T cells, macrophages, just these two, T cells and macrophages. Okay, antigenicity is the property of recognizing a certain microorganism as being antigenic, as being a foreigner that should be destroyed, and the way usually it alerts the immune system by alerting by antibodies or okay, where is it? Antigenicity, yeah, by bringing in, making the B cells become plasma cells, and multitudes of antibodies are going around, tagging in the invader and preparing it for the macrophage to be recognized. When macrophages are alerted to the scene of the crime, so to speak, what they do is they can cytocytose, they can swallow microorganisms and try to digest them, but it's more effective to get the T cells in. So what they do is they secrete IL-12. IL-12 move around in the vicinity, and when T cells make contact, physical contact with macrophages, or with particular gene on the membrane, MHC2, macrophages, and under the influence of IL-12, they become activated. These are the CD4 cells, or more specifically the so-called Th1 cells, CD4. These guys are going to, they are not very big killers, they are mostly scouts, scouting around. CD4 are mostly non-killing, not really good killers. In fact, being scouts, they move all over the body, and these are the guys that HIV virus tries to kill, by the way. Once you kill the guards, you can enter the city, so to speak. Okay, CD8 are those that are really going to fight, big fighters. They're also called cytotoxic T cells. And the way they are activated is by the CD4 cells. CD4 secrete IL-2, which is going to activate the CD8 cells. Okay, so we're going to deal with CD8, IL-12 will come in, and macrophages. Okay, so let's see. The CTL, when the cytotoxic T cells are being activated, they produce IFN gamma. IFN gamma goes and activates more macrophages, and they're going to also activate the killer cells, which is a different kind of killer cells. Okay, they are those that kill cells. Then there is the other, okay. Now, if there are too many of the T cells, macrophages, they are very toxic, cytotoxic. Too much cytotoxic can kill us. In fact, sepsis, which is the biggest reason for people dying at the end of life, end of diseases, is because of toxicity or blood poisoning. And there is, therefore, the body has produced a kind of cells that are going to block the activity of these cytotoxic T cells. These are the T regulatory cells. Okay? So they are also going to appear. You will see T regulatory cells coming in. Cancer likes Tregs because they are going to block the T cells, the CD8. So Treg, good for the cancer, good for anti-toxicity. So the question is always the proportion. Okay? And so the T cells, they are good for the cancer. Cancer would like to activate T regulatory cells, and it does it indirectly, and you will see how. No, we talked before, I think this morning we will talk about gene therapy. And here we are talking about immune therapy. And there is interesting, it reminds me, there was an article appeared in Science by Steve Rosenberg last week about a woman that had cancer in the bile, in the duct of the bile, going from pancreas to the liver. And life expectancy was about 2 months. There was a trial going on, a clinical trial, and in desperation, she asked to be involved in it. So she checked into this. What's a medical school, medical hospital at Harvard? Harvard, but what's the name of the? Maybe Dana-Farber, yeah. Anyway, so what they did was they took T cells that were in the vicinity of the tumor already metastasized into the liver and to the lung. They took T cells from the vicinity, cultured them. They first took find out what mutation she had, and then they took T cells, cultured them accordingly, and injected to her, and is a large amount. I don't remember how many, but a few, 1 or 2 or 3 gallons of this. Over a period of time, she lost her hair, but the tumor disappeared for 6 months. Then it came back. Then they checked the T cells again. They call them invading T cells. They are some kind of the CD8, but with a certain kind of special phenotype. And they found that 25 of these T cell invaders were actually active. The rest were not doing anything with the tumor cell. They took these, cultured them again, and injected now this time twice as much. And the tumor has disappeared now for more than a year and a quarter. This was a case that was published in Science. And the question is it just one person? Or is it something they can use in terms of immune therapy? So that's a kind of thing that eventually cancer immune system is going to lead to. So I guess I took a break here. Are you counting the minutes? Because I'm going to take more than 50 minutes. This story was not in the part of the...
Oh, no, there's no such a thing.
Okay, so IL-12 is a... So you can think that IL-12 should be a good anti-cancer therapy because it's going to alert very directly the CD4 T cells and then the CD8, but it's too toxic. So that's why, although it could be a powerful agent, but it's too toxic. Although there are right now one clinical trial, they try to see if they can deliver it in a way that will be manageable. So people turn to IL-27, which is less toxic, and ask, is this going to be used instead as anti-tumor agent? So we are working with a guy who does mouse experiments and with IL-27, and we're trying to, first of all, develop a model that agrees with all the medical data, experimental data, and then use it to cure mice. Hopefully, it will suggest how to cure people. Of course, it's not the same thing, but you have to start with this experiment on mice and not on people. So Okay, so here is a simple model that we developed. So you see there's the cancer cells. Now, in order to see how IL-27 does, we have to transfect mice to inject to mice cancer cells that are transfected with IL-27. So there'll be a lot of IL-27, we can see the effect of it. Otherwise, because cancer cells don't usually produce very much IL-27, some of them don't do it at all. These are particularly melanoma cells. So that's why they are secreted a lot of this. And then IL-27 being somewhat toxic, but anyway, the toxicity, it activates CD8 directly. Now, CD8 secretes IL-10. When macrophages secretes IL-10, it's non-inflammatory. When CD8 secretes IL-10, it is inflammatory, which makes the biology a little complicated because you have to see where is the cytokine coming from. It's not the same if it's produced in a different factory. Okay? IL-10 blocks cancer cells. CD8 also secretes IL-F gamma that will lead to blocking of the T cells. But now, since IL-27 is not completely toxic, it inhibits, not block, but inhibits the production of IL-F gamma by T cells. So it does one thing, but it doesn't do it wholeheartedly, so to speak. It tries to inhibit IL-F gamma. So that's the model that we looked at. And this is a system of equations, which I'm not going to go into details, but let me just point, let's see, where is it? Okay, there is the cancer cells. So they are, here you see, we didn't want to introduce IL-10 directly to make it more complicated, so we said macrophages secretes IL-10. This will be the inhibition of IL-10. This will be the killing rate of IL-12, of the CD8. So we are sort of having a representation of cells in direct way. Surrogate presentation of IL-10 and IL-12. Okay? And the production of IL-27 is here. See, this is large in our experiments with the mice that have been injected with transfected cancer cells. And, okay, there is the T cells. They are killing, the T cells are killing, where is the C? There is the cancer cells. They are being killed by T cells indirectly by, so IL-gamma, and by the IL-10, which was, oh no, this IL-10 is a toxic one, which is killing cancer cells. Okay? So now simulation of the model. So you see here, let's see, where is the cancer cell? C, here it is. Okay. So this is a control mice, okay? So the mice are JMM5 and they are controlled. No injection of IL-27. The volume, the total mass is increasing over a period of 80 days. If you are giving now the IL-27 at increasing levels, you see the level of the cancer goes down. Correspondingly, the T cells are reverse. If you don't do anything, there is very little T cells because IL-27 is not there, so and so on. So these are simulation results that are qualitatively agree with experimental results. So just to show that one can do something with this, we are testing here. Here is trying to do the simulations, not total amount of cells, but how they are distributed along the radial. So we have a radial tumor, radially symmetric, and we want to see how they are distributed as the tumor progressing. So there is the end of the boundary of the tumor. And let's see, here is the tumor cells. This is after 15 days And you see here, if you don't give anything, this is a level distributed in time. They are moving, the front of the tumor is moving. And if you are giving the total a larger amount, it's less tumor cells. The front doesn't change very much. If you want to see what happens here, then this is a magnification of it. Okay? Why is what?
Why is the spatial aspect?
Because you want to see how the tumor grows. How it,
Yeah, but you can just count the cells.
count the cells?
Yeah.
And we don't work with individual cells. We work with density of cells.
Okay, but still, I mean, this density you can still measure without spatial aspect.
The density.
I mean,
We want to see how it's distributed as you move along.
yeah, that's what I'm trying.
Oh, you want to go to OD? Well, okay, we'll try to do it. We'll try to generalize it.
If everything is off,
Well, tumor lives in space, so we need the space to see where it's going, especially if you talk about later on metastasis. So here is where we give a drug which is injecting of IL-27, you see. And now the tumor cell doesn't produce very much. As I said, it does not produce the IL-27. We inject it as a drug. And this is a model of distribution in space to take care of the chemical dynamics of the chemodynamics of the pharmacokinetic of the drug. Okay, so as you go into the depth of in the core of the tumor, the R gets small. The total amount is what you give is F, and it's distributed is in a way that it is less in the core and more on the boundary. But we also look at intermittent, just to see what happens. You give intermittent injection of total amount, but injected intermittently. What we find is that continuous one is preferable. If you look as a C here, so there is intermittent one, and the one that is continuous, total amount is same, but in continuous, it stays a little bit below. And when you stop the drug, so it goes back to the original tumor, but a little bit later. So it's some improvement, not very much. Yeah, you only slow down the growth. It's not, by itself, it does not block it. Not so far, no. Also, the experiment showed it's not completely. That's another one, a sample where you gave I should say, okay, there's more of this. So I should say one thing about it. So because we heard about oncolytic virus earlier. So now, it's not here, but in the work in progress, we are now injecting the IL-27 by a virus in the thigh of a mouse. And it goes in to do the same job. But it turns out the IL-27 does a bad thing. So it fights the tumor on one hand, but it also does something bad. What it does is, so every T cell has on its boundary two types of proteins. One is called PD-1, which is program death. The other is PD-L1, which is a ligand to program death. PD-1 is always activated. Also on cancer cells, there is PD-1, but not PD-L1. PD-L1 is also only on T cells. What IL-27 does, unfortunately, is activate the PD-L1, which means on the same tumor cell, you'll have PD-1 and PD-L1 activated. And think of a bunch of such cells together, they are certainly going to connect the ligand to the receptor, and therefore the T cell will become inactivated. When PD-1, PD-L1 complex is formed, the T cell is inactive. So it doesn't do the job. Therefore, now there have been experiments, now collaborators with experiments of co-therapy injecting IL-27 and also blocking PD-L1. And it turns out it's like a seesaw. Depending on the amount, it's either cancer progresses as it was before, or progresses less, or partly inhibited by this amount. And that's something that we are going to try to model. So that's a IL-27. Okay, now I'm going to IL-35. So IL-35, here is a family that I did not mention before. So this is a family of the IL-12. So IL-23 is highly inflammatory, and it was applied to cancer, and it turns out in some tumors it is bad for the tumor, in some it is good for the tumor. So people say IL-23 is controversial. And the experiments are not that wide enough to be able to classify, to see ahead of time what's going to happen. So IL-23 is, let's say, controversial. IL-12 is highly inflammatory. This is going from more inflammatory to less inflammatory. The reason they are all in one family, of course, because they have the same basic protein structure and differ only with some additional changes here. IL-27 is mostly inflammatory, and IL-35 is anti-inflammatory. Anti-inflammatory, which means that we are going to try to block it if we want to fight cancer. So now I'm going to come to this. Okay, so there is IL-35 going to come in. So the T regulatory cells are, they are in the environment already, as you will see in a few minutes. What they produce is TGF-beta, tumor growth factor, which is a highly active molecule. It comes almost everywhere, and it's multifunctional. It has all kinds of things it can do. IL-10, which in this context now, it will be anti-inflammatory, and IL-35, which is anti-inflammatory. And we want to focus on IL-35. So being anti-inflammatory is going to disable activities of T cells. So we want to block it. Okay? So blocking IL-35 will be as a therapy. How much time do I have, by the way? I'm sorry? 25. Oh. Okay. I hope no one will object if I finish early. Okay. So, here is a picture. Now, let's go over this. There is a tumor cells. And as before, in this experiment with Dr. Bai, what he did was he transfected tumor cells with IL-35 cells, cancer cells, so they'll produce a lot of it, and they will see what IL-35 does. Once we know what it does, we'll try to block it. Okay? So that's why, so this is what happens. It produces IL-35. Now, IL-35 is going to bring in the mouse experiments, it's going to bring in the T regulatory cells, but the tumor has also a different way of introducing IL-35, which, so in the mouse experiment, this arrow was very significant. But when we eventually want to apply the drug, anti-35, to mice that have tumors, we're not going to transfect them. We're not going to make the mouse is what it is. It doesn't have in its body an anti-IL-35. So, so the way it produces indirectly is this. The tumor cells are known to secrete MCSF. Okay? MCSF is known to upregulate the differentiation of myeloid cells to myeloid-derived suppressor cells. And these include macrophage type cells, anti-inflammatory macrophage type cells. Okay? These cells are going to produce, these cells and the TGF-beta, which is also produced by cancer cells, also produced, together are going to upregulate T regulatory cells. So that's how the tumor brings in the T regulatory cells. It goes in this way. MCSF, MDSS, production of TGF-beta, IL-10, and the TGF-beta. So the tumor secretes TGF-beta, MCSF, and eventually you get the Treg. That's the way the tumor tries to fight for its own growth. Okay, now the TGF-beta, let's see, where is, yeah, the MDSC, which the tumor likes to help in bringing in T regulatory cells, they also secrete MCP1. So major chemoattractant protein. These are cytokines. These are actually chemokines. They are chemokines. They are cytokines that bring in macrophages by chemotaxis. So here, as MTC brings in macrophages, and the macrophages, I already mentioned before, that macrophages are talking to CD4 cells, and CD4 cells are upregulating CD8 cells. So inadvertently, the tumor tries to bring in regulatory cells, but at the same time, our system is such, or the mouse system is such that CD8 are going to come in. So that's a kind of interaction, crosstalk between T regulatory cells and CD8 cells. Now, Treg don't like to see too much toxicity and try to block CD8. How do they do it? They produce also TGF-beta. TGF-beta inhibits CD8. Now, to say something about, everyone has to say something about VEGF, right? To make Tracy happy. So, tumor cells secrete VEGF. IL-35 helps in this, enhances this secretion, which bring by chemotaxis the endothelial cells and therefore also oxygen. And oxygen is a source, you see, to the tumor. So that's a way by which IL-35 helps the tumor. Another way it helps the tumor, once in bringing T regulatory cells and another in helping with the VEGF. At the same time, as I said, a side effect of this activity of the tumor is bringing in the MCP1 macrophages and the CD8 T cells. So that's a sort of a very complex war actually between those that are for the cancer and against the cancer, and it's not clear where the loyalty of each cytokine is. Okay, so we try to model it, and here it's very important to choose estimate parameters as carefully as we want to, otherwise we'll get the wrong results. So there is a system, and let's see what is worth here to talk about. The cancer cells, okay, they are killed by CD8. They need oxygen here. Where is it? Here. They need oxygen to proliferate. These are the MCSF. Macrophage, something stimulate factor or something. Complex, okay. And there is, these are the MDSS, which are critical because they have two phases. One hand, they are going to bring in the Treg, and the other they're going to bring in the CD8 indirectly. And although this was very complicated, since if we can reduce and have some surrogate variable to replace the IL-10 or the IL-10 and what else? I don't know if TGF-beta is going to be there or not. That would be good to do, so we reduce the number of parameters that are in question, that need to be so-called estimated. So let's see, so we did replace the IL-10 and the TGF-beta. These are the regulatory T cells that are working in favor of the tumor. Now there must be more equations. Yeah. Okay. Oops. Okay, so where am I? Okay, here we are. So here are the TGF-beta, okay, and you see it's produced by Treg. There is a VEGF, which is promoted by IL-35. You see, if there's no IL-35, it will only be K1 over sigma H, which is a number less than 1. If there is IL-35 very, very large, it will be K1 over... if there is very little of it, it will be K1 over CH, which is less than 1. If there is very large of this, it will be 1. So it's going to go up from this small number, K1 over sigma H, has to be small, to a large number, which is 1. Okay, these are the endothelial cells. These are the chemotaxis of the chemotaxis by VEGF. This is a Heaviside function. The effect on endothelial cells has a threshold, H sub 1. These are the oxygen. I think these are all the equations. Okay, so here are simulations. I didn't talk about boundary conditions, but there are no flux at the end of the far away, and in the center, of course, spherical radius, the first derivative is always 0. Yes? What's this? Yeah, so the first derivative, as I said, actually it's not a singularity because it's in the space, and because at the center everything is regular, going in every direction has to be the same. That means the first derivative is 0.
Yeah, but when you make it, you cannot solve it.
Why not? You cannot simulate? Why not? Okay, so here are we see what is, okay, there is the cancer cells as we move in space. In 2 weeks, 4 weeks, 6 weeks, 8 weeks, you see the difference starts to increase. And this is when we don't block IL-35. This is when we block IL-35. So these are simulations that fit with the mouse experiments.
Are there data somewhere?
As a what?
Are there data somewhere on that time? Or
Yeah. Oh, see, this is a control, the red ones, so you don't give any drug. This is when you do give drug, the dashed curve. This was the initial position of the tumor. And as you see it start to progress, it remains low here because not enough oxygen is coming. The parameters, I didn't list the list of 2,000 parameters there, but, but it took several months at least to try to get the estimate as much as possible from the experimental literature, and then estimating a sort of and tuning up so we get as good fit as possible with the experiments. Yeah.
I wanted to avoid a question about how you got your parameters, so you removed the slide.
So yeah, but yeah, there are, you know, I mean, you can just count, you know, on the average there are 3 parameters in each equation, 20 equations, 60 parameters.
How did you get it?
Some of them you can deduce, like, for example, if you want to know the decay of VEGF, it's experimental result. You want to know the oxygen intake, that could be basically experimental results. Let's take something else. If you want to know this parameter delta M, there is no way to get experimental results, especially because, yeah, we have to, because we replace, yeah, it's indirect, you see, indirect. It's indirect by MDSC. Indirect, I mean, how can we get anything? So we try to say, estimate it. How do we estimate? Well, each one, there is a short paragraph of 2 sentences, or maybe sometimes 4, or sometimes we say we take, or sometimes we say we assume, depending on the amount of but there are parameters, and of course later on we do sensitivity analysis to see that things don't really radically change, and they are sensitive but not very radically change. But that does not prove that these are the right parameters. But this shows that these parameters can explain the data, and therefore they should be taken as a good direction where to extend the research, the experimental research. So, so such parameters, we have some leeway, and when we try to simulate it, we use those parameters that we have some leeway to adjust. So that really takes time. It depends. That's really, I was talking with Jan Kwang about it. It's really where it's important to do computations very fast, because there are lots of trial and error. This could take hours, and it could take months, depending how fast one is. So it's really okay. So now we go to simulations here, and there is simulation on the total amount. So let's say where is the cancer? I want to find it. Just here. So this is when, with a control case, you don't give anti-IL-35, you don't block it, and here you block it, and you get a lower increase of the tumor. If you want to see what happened to regulatory T cells, you see that there are more Treg here, and that's why there are more Treg here, which are less Treg here, which is good to fight cancer. You don't want to have T regulatory cells. So there are less of this and less of this. The T cell, CD8 will be more. I can only find it. T cell. Here we are. Okay, it's the reverse. So now we are going to give a drug. Okay, now this drug is anti-cancer. It's inhibiting. It's not that we are adding, we are inhibiting something. Therefore, in terms of modeling, it appears as 1 over the production of IL-35. This is the production by MDSC, by regulatory T cells, and a little bit by the cancer, but mostly by T regulatory cells. And this is and again, the pharmacodynamics tells us how the injection should distribute itself in the spherical tumor, less in the core and more on the boundary. And as we give the drug, you can see the dashed curve. The intermittent is dotted. You see the intermittent one. It's not as good as the continuous thing. And if you block completely the IL-35, which you cannot really do, but if you could, you will get this. So you see that even if you block IL-35 completely, the tumor will still grow, which means that it's not, this drug, if you use it, it will not regress the tumor. You need something else. So, the conclusion. Oh, yeah, I have only 2 minutes. Anyone wants to take my extra time? It's like in the Congress of the United States. I'll give you some time. I'll defer to the honorable. Okay, so here we are. What we did was developing a model of treatment by IL-27 injection or IL-34 inhibitors. We want to make sure that the model simulation agree qualitatively with mouse experiments. Okay, so, and that's we think we have achieved. The simulation, then we want to show the simulation for something because we have a model, and it's, well, I mean, it shows like the experiments, the same thing, but we already know about the experiments, so what does the model tell us? It tells us about intervention. So here we just saw how we intervene with this directly with 2 drugs. Of course, we could have intervened maybe with some other parts, like with TGF-beta. There are lots of or TGF-beta inhibitors using in cancer. Pancreatic cancer, for example, TGF-beta inhibitor is very popular. So the model can give us more. What will happen if we do this? But I guess the guy we're working with doesn't have enough money to do all that. So he has a mice, and he knows how to do with this particular injection. But to block anti-beta is more complicated. So, oops. So here we have a suggestion, but you see the effect does not have a long-term effect, and also does not have highly significant effect. Well, that's effect. It's something good to know about IL-27. If you want to use it, you need another drug. As I said, right now we are looking about trying to do PD-L1 blockage, so that the protein, the death signaling protein and its ligand will not be able to work together to silence a T cell. So that's another possible core therapy. Okay, and then okay, that's another drug, and yeah, okay, and Th17 did not come into play here, but it's something that may need to be taken also into account. So thank you very much.